Just to review at the end of last time, we were talking about nodes, and a node was just like a container. It's not an ADT, it's not data structure collection, it's just a container that we're going to use in a way similar to arrays, where an array just stores data and we're going to use the array as the thing that's storing the data for a stack or a queue or etc. But the trick with unlike arrays, the trick with nodes is the nodes don't have to be in sequential memory. I mean, neither do arrays in Java, but traditionally speaking, they are. A node is just some object that has a reference to data and a reference to another subsequent node that may or may not be null if it's the last thing in the list or the link structure. But remember that head or first, or whatever you want to call it, head is a common name, for the node at the very beginning of the link structure. So be very aware that head itself is not a node. If you want to instruct the node that had references to do anything, that's when you say like head dot something. If I'm saying, this is all within a big warning here. There's a big difference between head equals some node and head dot set next some node. So if I have an example that looks something like this, head, assume head was referencing this node. If I said head equals some node, well, head just, we update the reference variable head to reference the same thing that the reference variable some node was referencing. They're just reference variables. If I wanted to set heads next to something, I have to tell the node that had references to do something. That's where I say head dot set next to be some node. So heads next will actually be referenced, well, will actually reference the same thing that some node references. So just be aware of the difference here. Are there any questions about this? Or does anyone not see the nuance here? Because it's very important. All right. And of course, there really is nothing saying, like everything I've said so far is each node has a reference to its successor and some data. But at the end of the day, there's really nothing saying I couldn't have a reference to each node's predecessor, and then I can have what we call a doubly linked structure like this. Each node has two references, a next and a previous. And suddenly it becomes, you can traverse that link structure in two directions, forward and backwards, which is really great for several things. But of course, there's a lot more bookkeeping that needs to be done. It's not, I don't want to say it's trivial bookkeeping. It's definitely not too bad. It's not like overly complicated. But there is extra work involved to have a structure like this. And we always have to ask the question, does it actually give us any real value? But there's nothing saying we couldn't have something like this for our link structures. Any questions about these nodes? I believe this week's lab, let's just double check right here. Stacks, link structures. So this week's lab is all about building these link structures. Now that we've talked about these link structures, and you'll play with them in lab, we'll actually use them as a container for a stack. So we already wrote a stack. We already implemented a stack called array stack, where the underlying container was an array. But that's arbitrary. I mean, we could use whatever container we want to build the stack. So let's do it again with a link structure. We're going to build a stack again. We're going to implement the stack interface again. But this time, without an array, we'll do with a link structure. So what do we need? Well, we need a way to hold on to the data in the stack. That's where the link structure comes in. The data in each node will be the data. We need a way to keep track of the top of the stack, right? Because the top of the stack is always where the action's happening. All adding and removing takes place at the top of the stack. So we need a reference to the top of the stack, which is going to be like the containers, the link structure. So we have to think about that for a moment. And then we need an add, we need a remove. So our push, our pop, our peek, which is like remove, but we don't actually remove the thing, we just return a reference to it. Size is empty. ToString equals, those ones as well. But that's what we got to do if we want to implement a stack. Because remember, the interface defines what a stack can do, the what. The implementation is the how. We already have an interface. We already wrote an implementation. Now we're just going to do a different implementation. So, we push pop peek as empty size, implementing a stack with a link structure. So here's the idea. Here's a general view of what we're going to have. This is what we're going to try to build. So this is an example of a stack S that has 4 elements in it. S is just a reference variable to the stack object, referenced by this box here. And that contains a size, the field size, to keep track of how many things are actually in the stack. And it also is going to keep track of the top of the stack. Now, if you look at how this stack is being used, top is just the same thing as head. Top is a reference to the beginning of that link structure. Whenever we want to push something onto the stack, well, that's just adding to the front of a link structure, which we looked at last lecture, like last topic. Whenever we want to pop something from a stack, that's just removing from the front of a link structure. It would be, we could implement a stack such that the top of the stack was like the end of the link structure, but that would be kind of silly in terms of every time you wanted to add something, we'd need to traverse the whole structure to get to the end. Every time we want to remove something, we've got to traverse the whole structure. So here, we'll just, we'll keep track of the top of the stack, the beginning of the link structure, and all the action just happens at the front of the link structure. That's how we're going to implement it. Again, we could do it such that the top was the tail of the link structure, but that would be a lot of extra work. Like, we would be going out of our way to implement it that way. There's nothing wrong with it in terms of functionality. It will work, but it's not a great implementation idea. So this is the strategy we're going to go with. Any questions about this idea? All right, so if I'm saying push this light blue one on, well, we just insert to the front of the link structure. If we want to pop, remove from the front, pop again, remove from the front again. Here, let's go back real quick to the previous topic. And remember, adding to the front of the link structure, so this, if we're thinking in the context of a stack, what are we going to do? Well, pretend head is a reference to the top, so it's just called top. That node reference variable, the blue node, this is the thing I want to push. So all I say is node.set next to head, or top, and then top equals node. That's adding to the front of a link structure. Right? So node, set your next to what head is. Head, reference the same thing node references. There, we just push something onto the stack. Removing, that's the easiest thing there is to do. Just head equals head dot get next. So get heads next, which is a reference to the yellow thing, and have it reference it. So it's always just adding and removing to the front of this link structure. That's great. This is going to turn out to be rather, seemingly at this stage, a rather straightforward, simple implementation. But, we'll see. So let's look at our implementation. So here's the start of some class I have here. You'll notice the imports are missing because whatever. But public class link stack T, it's generic, because remember, generic is just a way to say I want to have any arbitrary type on here. If I want a stack of integers, I want integers on the stack. Strings, I want strings, right? And it's going to implement the stack interface because, I mean, we don't have to implement the stack interface, but then we're losing out on a lot of the value that object-oriented design gives us. When we implement the interface, we are guaranteeing that anyone that uses the linked stack is using a stack. So we implement the interface, and we have two fields, top and size. Top is just going to be a reference variable to some node, and size is just some integer to keep track of how many things are actually in the stack. And then there's a constructor, linked stack. Whenever we make a new stack, it's going to start empty, meaning that the top is null, there's nothing there, and its size is 0. Notice there's no static constant, no final default capacity, because default capacity mattered for the array. There is no array in the linked stack. There's no, we never have to ask the question, how big do we want our array to be when we start? That's not a thing right now. There's no array. So we don't need that constant here. And on top of it, we actually only ever need one constructor. Remember the array stack had two constructors, the default one and the one where you specify the default size of the array, or like how, not default size, but the size of the array. That doesn't matter anymore. It's a linked implementation. There is no array. So just one constructor. Great. Questions so far? Remember, don't be nervous about asking questions. It's really boring just talking at you for a while. Ask questions if you have questions. It's more fun for me. Yes?
So is, like, the link structure, is that a thing that's already made? Like
Nope. We have to implement a node class, right? So this assumes that we have a node class written. Yeah. Good question. The array we got for free, there's no nodes. Fortunately, it's like a 20-line class to make your own node object, but. Other questions? All right. Like the array stack, the interface constructor creates an empty stack with nothing on it. So what does a push look like? Now we've got our at override. Remember, that's only because it's overriding something defined in the interface. That tag there doesn't actually matter. We don't need to include it, but I'm including it because it's nice to the compiler. And what do we have to do? Well, if I want to push some element of type T onto the stack, and remember our push is going to return a Boolean, true if it was successful, false otherwise. With this particular implementation, it shouldn't be possible to have a failure on a push. So it will always return true. But nevertheless, it's pretty typical to have a collection to return a Boolean when adding and removing where necessary. What do? We want to push the element. Now remember, element is the data we are adding to the stack. The nodes themselves aren't important to the, how do I word this? The node is just the container for that one element on the stack. The data is what's really important here. Just like the array, in the array implementation of the stack, obviously the array was important because it's where we put the data. But if you're using a stack, you don't give a shit about the array. You just care about the data in the order it went in and the order it comes out. That's a stack. Same thing here. The person using the interface of the stack doesn't give a shit about the nodes. They don't care. They want to add data and remove data. So we have this element I want to add to the stack, but we got to put it in a node. Remember, the node isn't important here. It's important for the implementation, but not for what a stack is. It's just the data is what's getting added to the stack. But we need a node because that's where we're putting the data. So we make a new node with the data we want to add to it. We called it toPush because I think that's a decent name for a node we want to push onto the stack. Well, really, it's a node containing the data we want to push onto the stack. And then this code is just adding to the front of a stack. toPush, set your next to the current top. It may or may not be null, but it doesn't matter. Like top may or may not be null. And then top references to push. That's adding to the front of a link structure. That's all that is. Increase size, because we added something to the stack. Return true because, well, it needs to return a Boolean and it's not possible for this add to ever fail, this push to ever fail. Any questions about this push here? Just think about it for a second here. The node is just the container, so we put the data we care about into the container. This is the new top, though. It should become the new top. So that node references the node that contains the data of the old top. And then top updates its reference to the new node that we just created. Increase size, return true. I really can't tell by the look on your faces if you're happy or sad. One thumbs up. You speak for everybody. Thank you. Pop and peak. Well, pop. Well, let's look at peak first, because it's even, yes?
Wait, pushes to add, yeah?
Yes.
What happens if it's full?
What happens if it's full? Should never become full. Unless we wrote the stack such that there is a hard cap on the size, where I can say, like, I never want to have a stack that has more than 1,000 things in it. Otherwise, I could just arbitrarily create more nodes and have them reference the old top and keep stringing these link structures on forever and ever and ever. It is possible that we do run out of RAM eventually, but that's going to be a pretty unusual situation. It could happen. Probably shouldn't happen in 162. It could happen. And if that happens, well, the whole program will crash. You'll get like an out-of-memory error. I believe it's an error, which is different than an exception in Java. Exceptions are like recoverable situations. Errors mean like, well, you're screwed. If you ever get an error, it's nothing you could actually solve programmatically. It's like a Java issue. Were you going to ask about what about RAM? Could you run out of RAM? You could, but probably not. Yeah. If that happens, well, chances are you've done something really wrong. I mean, you could create a loop to go to like 10 billion and just create new nodes to just keep getting inserted to the front of the link structure to create this hilariously large link structure. You could do that. Have fun. Yeah.
Is there any reason because of the limit on your stack?
I can imagine, in general, no, but I can imagine that there might be a place where I say, look, in my particular implementation, there should be no more than, like, let's say it's like a video game or something. There should be no more than 16 players, and I'm keeping track of the players in a stack for some reason. And then I can just set a hard limit. But in general, I can't think of one. But I'm sure someone can come up with a reason why it would make sense for them. Yeah. Other questions? I thought I saw another hand pop up and then disappear quickly. All right. Let's look at peak first before pop because it's easier. With peak, remember, it just returns a reference to the data at the top. Usually, and I know I've said this before, in general, when you have a collection in Java, your add and removes return Booleans to indicate success. But a stack is a special type of data structure where, well, when you remove, calling remove like returns that thing. So it's not the general case. So peak returns an element of type T. It doesn't return a node. The person using the stack should not have any care in the world about nodes. They don't care about nodes at all. You on the implementation side of that interface cares about the nodes. But anything that they get, they should never see the nodes. The nodes is an implementation issue. It's an implementation detail. So it returns something of type T. If it so happens that the stack is empty, which we haven't written that method yet, but I'm imagining you can concede that it will exist. So if it is empty, throw that exception. No such element exception, empty stack. I gave it a message, so if we see this exception, we see what happened. Otherwise, go to top and get the data and return it. I'm returning the data, not the node. The node doesn't matter. The data matters. And now similarly with top, if it's empty, you throw an exception. Otherwise, get the data we want to return from the node at the top. Top equals top.getNext. This line, that's removed from the front of a link structure, right? If I have a link structure, if I'm the top and I'm referencing a node, and I say, hey, node, what's your next? That gets me a reference to its subsequent node. And then I just overwrite me to be a reference to the subsequent node. So that's what top equals top.getNext does. That just removes from the front. We decrease size. We return the element. Could I do this in a different order? Could I access the element after I update the front? I mean, I could if I created an additional reference variable, I guess. But I would be working really hard. Because as soon as I say top equals top.getNext, I've lost reference to like the old top, containing the data I want to return, which means I can't access it, which means I can't return it. I'm screwed. So that's why it's important that I actually got the element I want to return from the thing at the top, saved it, updated the top, then returned the thing I wanted to return. Again, I'm returning the data. I'm returning something of type T. I'm not returning a node of type T. It's the data I'm returning. Size and is empty. Well, size just returns size. Is empty if size is 0. Return the result of asking the question, does size equal 0? Can anyone think of another, based on the implementation you've seen so far, can anyone think of another reasonable is empty method, how it could be written? Pardon? If top is null, yeah. If top is null, it's empty. Both would be equivalent in terms of doing what it needs to do. I just did it this way for consistency with the array implementation, but I could have said if top is null. It's the same. The size is 0 when the top is null. That must be the case if everything was implemented correctly. It should never be possible to have a size that's not 0 while top is null. ToString. Well, it's very similar to the array one, but remember I wanted the top to always be. Remember with the array implementation how the array implementation, I had an array starting at index 0 and I would build the stack out like this way, right? But remember how when I printed out the stack, I wanted the thing at the end, which was the top, to be the first thing printed out. Do you remember that? Hopefully you do. If not, well, that's what we did. So I always wanted the thing at the top, which was always like at index x, right? Not 0. It could have been 0 if it was like the only thing on the stack. But remember, the bottom of the stack was always index 0 with the array implementation, right? But when I printed it out, if I printed it out such that the bottom of the stack was first, imagine that ToString. The bottom would be here and the top would be however far down the string. Right? Are you following me? So I wanted to do it the other way. So when I did my ToString, I kind of built the string in reverse. I always, instead of taking a string and appending to the end of the string, am I doing that right for you? Yeah. Appending to the end of the string, I built the string and kept prepending, right? So I started at the bottom, went to index 1, index 2, index 3, 4, 5. So always the last index was always the thing at the front of the string. Remember that? But here with the linked implementation, it's reversed, right? The top of the stack is the thing that comes first in the link structure. So now I don't need to do any prepending. All I need to do is traverse the link structure and keep appending to the string I want to return, or appending with the string builder object, which is a nicer way to do string building in Java. So I could just build it normally. No funny prepending stuff that I had to do with the array implementation. And notice how I iterate over a link structure. This is your common strategy. First, let's look at the whole thing. Create an empty string builder. Remember the string builder. Raise your hand if you remember why we use string builder. 3 people. Okay, well, I'll say it again. Strings are immutable, right? Every time, if I want to append something to a string, can I ever actually append something to a string? No. I have to make a new string. So imagine I have a link structure of 1,000,000 things. This is going to have to make 1,000,000 new strings. It's kind of mean to your computer. That's a lot of work, right? There's a lot of overhead involved. So instead, we use a string builder, which is kind of just like a list that keeps track of all the individual strings, and then it appends them. It actually creates one big string in the end. It's a little nicer to your computer in terms of the amount of work involved. So that's what the string builder is. But a string builder object is not a string. That's why in the end, we say, okay, builder.toString, well, like every other toString, that returns the string representation. That's how you convert the string builder object to the actual string. But what's in between? Well, current node is going to be a reference variable to a node that's always going to be referencing the current node. We started at the beginning, which is top. And I asked the question, is current node not null? If it's not null, that means it exists. So I get the data, I append it to my string builder, add the comma space, and then I say current node equals current node.getNext. That's just how I move the reference variable down one node. And it just loops until eventually current node will hit null with this implementation. So that is your typical iterating over a linked structure. Iterating over an array, typically you're looking at like a for loop, right? From 0 to however many indices. With a linked structure, you go, well, my reference variable is not null. And instead of, imagine this was a while loop with an array. The last thing I would do in the while loop with the array would increment my index counter, right? Well, the last thing you do in a while loop when iterating over a linked structure is current node equals current node.getNext. Just move it to the next thing. Move the index counter down to the next integer. Move the node reference variable to the next node. Same idea. Equals in hash code. Well, so your equal starts with your okay, are they literally the same thing? Is it null? Or are they not even the same class? Otherwise, we have this and that. This is going to be a reference variable to the current instance, as it always is. And with my code, I called the other one that, because I thought it was fun to have this and that. And then I have 2 reference variables, this current and that current. Well, this current is not equal to null and that current is not equal to null. Check if the data and their contents are equal. If they're not equal, return false. When I'm iterating over collections, the moment I see unequal elements, I know they're not equal. It's like a linear search. But it's always well, what are you looking for with the linear search? With a linear search, you know the thing you're looking for exists the moment you find it. You can only conclude it doesn't exist after you've exhausted everything. But here it's kind of flipped. I know these things are not equal the moment I see something unequal. I can only conclude that they're equal after I've looked at everything and never found anything that wasn't equal. All right? It's kind of funny, but whatever. So whenever the elements don't exist, don't equal, return false. Otherwise, move this current and that current to the next one. If I could have written this a little differently, I could have checked by saying, like, are their sizes different? If their sizes are different, there's no need to even go doing any comparisons. Yeah, sure, fine, I could do that. Wait, no, I already did that. Oh, look at that. There we go. I already did that check, yeah.
Why do you use the question marks instead of like T?
I don't want to get into it. I was hoping no one would notice. So, generics are weird, and there's a lot of rules around them, and I don't want to get too far into the weeds. This is a particular case where, because of object-oriented languages and a bunch of funny little stuff, this is just kind of the way it has to be, and I'm not going to get into the details as to why. So for now, for your equals methods, you're going to see question marks. I think we see question marks a little later in the semester with some explanation as to why they're important. But it's kind of like a wild card of types about like, well, what if the T types don't actually match? I don't really care what the types are. I just want to be able to check their equality. And if their equalities don't match, well, then I know they don't match, regardless if they're both things of type T or if one's of something of type. They can both be generic, but what if one's generic type was string and the other one's generic type was integer, right? So, and as soon as you get to inheritance, it gets complicated. For the time being, this is the magic code to make it happy and shut up. I'm sorry, I always hate magic code. I avoid it as much as possible, but this is kind of the magic code. So that probably doesn't satisfy you. Deal with it. That's my answer for now. Did anyone else notice the question marks and thought, what's that? Okay, you're right, but don't worry about it, even though you should worry about it eventually. So yeah, the first thing I did is I actually checked their sizes. And if their sizes aren't equal, return false. I immediately know, obviously, they're not equal if they don't even have the same size. Now, you might say, you know, there's really no point to checking this. Their sizes are the same. Let's think of this logically about the state of these things. They both have the same size. They both have this current reference variable to reference the top at the start. And every time at the end of the loop, their reference variables are moved down to their successor nodes. Okay? If their sizes are the same, is it ever possible for this current to not be null and that current to be null? Is it ever possible? No, they have the same size, and if they're kind of like fixed in how they move together, it's not possible. So you might look at this code and say it's entirely unnecessary to check that they're both not null. All you need to do is check one of them because they are inextricably connected at this point. It's not possible for one to be null and the other one not, and vice versa. It's not possible. So there's no need to check both conditions. Who wants to say, who can tell me why I'm checking both conditions? It's not really a trick question. Some might argue it is, I guess. For me, it's just code, readability, and understandability. What do I care about? This is very explicit about what I care about. And someone can say, well, given if I really understand everything and given the state of things, it's not possible. There's no need for both of those checks. You're right. But that requires more underlying understanding. Where this code right here, I just find more self-explanatory and explicit about what I actually care about in terms of the intention of what I want. So that's why it's written that way. So the trouble is new programmers, and if this was 40 years ago, you'd be right. But new programmers have a bad habit of trying to optimize things that don't matter. And sometimes when you optimize things that don't matter, and even if sometimes they might matter in some cases, you might lose explainability and understandability of your code, which is bad. So don't over-optimize. And chances are the compiler will have caught what you noticed, and when it turns your code into the actual zeros and ones that your computer uses, it'll have made the change for you. So let the compiler optimize. You just write code. I always say it. Computer code is not for computers, it's for humans. Machine code, zeros and ones, and byte code, without getting into what that is, but zeros and ones, those are for computers. We just have a program, the compiler, that turns the code to the zeros and ones for you. But computer code is for humans, not for computers. So write it for humans, not for computers. Cool? Remember that, it's important. And then your hash code, it's the same as the array one, except I flipped out the loop for how I iterate over a linked structure, where current is not equal to null, do whatever, and then just move down the current reference variable down the linked structure. So far, so good? Now this goes to the question you had asked, like, well, where's the node class? Well, this assumes the node class already exists. But now, if you go and you download the code for the course, you will go and you will find where is it? A node class. There we go. The node class. It's right there, right? And it's sitting in my project, and you will also see the linked stack right here. So it's sitting in my project right next to the linked stack. The fact that they're next together is just, that's how the alphabet works. It's not important in any way. So it's right there. There's also a linked queue and a linked iterator, a bunch of linked things that make use of node objects. But we got a bit of a problem here. Now, what I'm about to explain is not some fundamental computer science-y thing. This is more of a project bookkeeping thing. The node class has the potential to cause some headaches for us. First, I showed you a node that had two fields, right? It had a data field and a next field. But I also showed you a potential where you could have like a doubly linked node where it has a data, a predecessor, and a successor, right? A next and a previous reference variable, right? But they're both nodes. And later in the semester, we're going to be learning about binary nodes, which are nodes that have two reference variables, but they're for tree structures, right? And you can have nodes that have even more reference variables. Node itself is a very general purpose name that can mean different things in different contexts. So when you have a class sitting in your project called node, another programmer can come along and look at that and go like, well, crap, what kind of node is it? I'm going to have to go look at their code and figure it out, right? Not that big of a deal, but it could get confusing because node can mean a lot of different things in different contexts. And further, the existence of the node, think of the linked stack class. It depends on the node class. But at this point in time, in spite of the fact that I can look here and say, well, but there's also a linked queue and a linked iterator and a linked this and a linked that and so on, they're all going to use nodes. But let's pretend the other ones don't exist right now and I just have a linked stack. The node class itself is only important for the inner working of the linked stack class. So remember, if we have a function inside of a class, or a method inside of a class, that's important to the internal operation of that class, but is not important, like I want it to be private. I don't want it to be accessible outside of this class. It's not in the interface. It's just expand capacity had to be there for the array implementation because it just had to be there for it to work. But no one using my array stack should give a shit about expand capacity. They just want to be able to push things on the stack and have it work. It only matters for the implementation. It's the same idea with the node class. The node object really only matters for the linked stack. And it really shouldn't exist outside. I mean, it could exist outside, but it doesn't need to exist outside in the same way that expand capacity could be some method written in some other class that I could use, but it makes sense to put it inside the class that's using it, right? So what I can do, instead of having a private method, I can make a whole private class that exists inside another class. And if we scroll all the way down, no, it actually doesn't need to be private. It could be public, but I'm going to do it private. But if you scroll down all the way to the bottom of this class, you will notice there is a nested private class inside. It's inside the class. It's not just in the same file. No, this class's code, its open squiggle and close squiggle, is completely contained within the linked stack class. So this ends the node class. This ends the whole linked stack class. When you look at this, it's exactly the same as if we go look at here, node class. This right here, it's the same as the one inside here. It's called private static class. It doesn't even really need to be static, but just it's there because don't worry about it. Excuse me. So now I've got this whole class and it's contained inside the link stack class because it's important for the functionality of the link stack, but not elsewhere. In the same way that we have a private expand capacity that's important for the functionality of expand capacity for the array stack, and it doesn't really need to be anywhere else. I didn't need to do it this way, but there would be if you were to take all the people on the planet who are programmers, who are experienced programmers, and say, which way should you do it? Should you make it like a private inner class or some external one? Most people are going to say, make it a private inner class. It makes sense. It wouldn't be wrong to do it the other way, but most people would say, this is better. So not just methods can be private, but whole classes can be private if they're simply important to the functionality of your class, which is pretty cool. And so every time I reference this node, it's using the internal class, which is neat. Yeah, okay, so this is me saying, okay, remember, well, we could have a doubly linked one. Well, it's called node, what do you do? Oh my gosh, it's kind of confusing. And there's this design philosophy, I don't know, I don't want to know. I don't know how the implementation of the link stack works. Obviously, look, every time I use this as an example, it's kind of cheesy in this semester because the whole point of this class, the whole point of 162 is to learn how these data structures work, to implement them. But go back and put your Python hat on when we were using lists in 161. You didn't know how a list worked. You didn't need to know. I don't care. I don't want to know. Just work. That's kind of the design philosophy. When it's your job to actually implement those classes, well, you can't really say, I don't know, I don't want to know, because, well, no, you're building it. Go freaking build it. But in general, when you think about that barrier of the interface and the implementation, if I'm on this side of the interface, I don't know, I don't want to know. I just want to know what, which is what's in the interface. To be clear, also, when I say interface, I mean the actual Java thing, interface, public interface stack. You can push, pop, peek, is empty size. But interface is also often used as a word to describe just any arbitrary classes, public methods, what you can do with it, how you interface with that object. So an interface is like an actual like proper like thing. And it's also like the country class's public methods from assignment 1. So we can do a nested class, yeah, cool. Any questions about any of that? We just blitzed through a whole new, new implementation of a stack in what, 20 minutes? Which might feel like a lot, but you're probably pretty good because we discussed the interface. We put a big effort of separating the interface, the what and the how. We already built the how, the array one. You already knew how linked structures worked, at least at a high level. You haven't really sunk your teeth into them yet. You will this week in lab. But once you have all that understanding, it just becomes a matter of, okay, use these ideas and just do it again slightly different. So it might feel like we blitzed through a lot of information, but it's because you already had a lot of context behind it. Now, I had mentioned this before about the whole, one of the cool pieces of value of using an interface and having things implement interfaces. When your class implements an interface, like when the array stack implements stack and linked stack implements stack, they both implement stack, meaning Java knows that they both push, they both have push, they both have pop, they both have isEmpty, peek, size. Java knows it has those things because they implemented the interface. Java also knows it has an equals and a toString because everything does. But both of those things both the array stack and the linked stack implement an interface. Now, when they implement an interface, there's no guarantee. Java can't guarantee that these things are implemented correctly. It just guarantees that these methods exist. And because of that, we get a huge benefit. Look at this code right here. Playing linked stack. You can download this from the course website. The reference variable's type is a reference variable to, its type is a reference variable for the interface. The reference variable isn't a reference variable to a linked stack, it's a reference variable to a stack. Now, the actual thing I'm creating is a linked stack, new linked stack, okay, go create a linked stack. But a linked stack is a stack. So the myStack reference variable of type stack is happy to reference an array stack or a linked stack. They're both stacks. And because it's a stack, I can tell any stack, I don't give a shit about which implementation is. They are stacks. If it's a stack, I can say, hey, what's your size? Are you empty? Print out the stack, the toString. I can call push, size is empty, push, size is empty, peek, size, pop. All of these, I know they exist, regardless of the implementation. They must exist if they implemented the interface, which Java guarantees at runtime because it wouldn't have compiled if you went to hit run before your linked stack or array stack actually implemented all the methods in the interface. How many of you, when implementing the array stack in last week's lab, was like, why is IntelliJ yelling at me? I haven't even started writing the code and it's saying I've broken it. It's because you didn't implement the interface entirely yet. That's how excited Java is to tell you you're wrong, okay? Actually, that was IntelliJ. But once it was all implemented, it's happy. It knows that those things exist. And you want to know something crazy? This code right here, this 68 lines of code, is absolutely identical in every way but half of one line of code to the example plain code I showed you in array stack. If I scroll down to the bottom, it's identical code except for half of one line of code. This is the array stacks one. if you have a billion lines of code that depends on stacks, and someone comes along and they're like, I invented a new stack that's way better. And if your first thought is like, man, I've got like a bajillion lines of code that depend on a stack. I'm going to have to go rewrite everything. No, you don't. If it's a stack, you go and you change half of one line of code. And suddenly you've switched out the whole implementation that you're actually using in the back end. Because it's a stack. And Java can guarantee that if this new stack implements a stack, it's a stack. And a stack can push, pop, peek, is empty, size, etc. And it's happy. And that's where the magic really starts to fill in with object-oriented languages like this. And this is just the start of cool shit like this. Where just by designing your code in a good way, Java just kind of like forces you to program in a really clean, nice way. Like you have no other choice. All right, I'll catch you later.